Hello everyone, welcome to Organic Spectroscopic Analysis course. In last lecture, we have learned the selection rule of infrared spectroscopy. In this lecture, we are going to learn the factors of influencing vibrational frequencies. The first factor is the status of a molecule. Frequency in gas is bigger than that in liquid and much bigger than that in solid. N-methylethylamine in its liquid state forms clusters, which makes carbonyl less stronger than that in solution. Vibrations of carbonyl group shift to a lower frequency as 1650 cm per second. For a simple harmonic oscillator, the frequency of a stretching vibration is given by an equation driven from Hooke's law for a vibration spring, where n is the Avogadro's number, c is the velocity of light, k is the force constant and a measure of the bond strength, mu is the reduced mass. Frequency decreases with an increasing atomic weight. Frequency increases with increasing bond energy. Electron withdrawing group makes the absorption peak shift to higher frequency. Due to the different electronegativity of the substantials, the distribution of electron clouds in a molecule is changed by the introduction effect, which changes the force constant of the bond and the characteristic absorption frequency of the group. The carbonyl group is a strongly polar group. Due to the large electronegativity of the oxygen atom, the electron cloud of the carbon-oxygen bond is approaching to oxygen atom. Generally, the force constant of the double bond is greater than that of the single bond. So any effect of increasing the form of the single bond or enhancing the polarity will reduce the force constant of the carbonyl bond and cause the stretching vibration frequency of the carbonyl group to move to a lower wave number. Conversely, when an electron withdrawing group is connected to a carbon atom of the carbonyl group, the polarity of the carbonyl group is weakened and the carbon-oxygen bond force constant is increased. And the absorption band moves towards to a higher wave number. Conjugation effect. Conjugation effect often causes the polarity of the carbonyl double bond to increase, and the double bond decreases and the stretching vibration frequency moves to a lower frequency direction. The carbon-carbon triple bond or carbon-nitrogen triple bond existing in the conjugation system, its stretching vibration frequency also moves to a low wave number of direction. In these examples, p-pi conjugation makes the vibration of carbonyl group move to a lower frequency, and pi-pi conjugation makes the vibration of carbonyl group move to a low frequency too. Field effects is not through chemical bonds, but the effect of electrostatic fields through space. In the three-dimensional configuration of the molecule, only when the interesting groups in certain spatial structure are close to each other will the field effect occur. The field effect not through chemical bonds, but the electrostatic fields of atoms or atomic groups interact through space. Steric effect includes ring force and staggering hindrance effects. The double bond outside the ring moves a higher wave number as the ring tension increases. In contrast, The double bond inside the ring moves to a lower wave number as the ring tension increases. The effect of steric hindrance refers to the presence of certain groups in the molecule when the steric hindrance affects a normal conjugation effect or hybrid state in the molecule, resulting displacement of a vibrational band. The introduction of a methyl group on the olefinic carbon prevents the carbonyl and the carbon-coupled double bond from being on the same plane. Therefore, their degree of conjugation decreases, and the double bond character of the carbonyl group increases. The vibration shifts to a higher wave number. Transcellular effects also influence the vibrational frequencies in infrared spectra. Due to the formation of hydrogen bonds, the force constant of the chemical bonds participating in formation of hydrogen bonds is reduced, and the absorption frequency moves to a low wave number. At the same time, the change in dipole moment during vibration increases, so the absorption intensity increases. When hydrogen bonds are formed in the molecule, the absorption frequency can be shifted to a lower wave number. As the concentration of the solution increases, the hydrogen bond association degree increases. The band shifts to a lower wave number, and the intensity increases and becomes wider. So in this lecture, we have learned about the factors of influencing vibrational frequencies. They are very important for interpretation of infrared spectrum. Thank you for watching.